Hey everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials and Manufacturing Innovation. Today we have a paper that comes from authors at the University of Buffalo, Sun, Marziale, Buehler, and Chen, and it has to do with additively manufactured niobium alloys. Okay, the authors jump in and describe the miracle that has been additive manufacturing in terms of turning out high-performance, interesting alloys and shapes and sort of speeds that we could have never done in the past. But the downside, they point out here, the persistent challenge is that the as-printed metallic parts often suffer from defects such as internal porosity. And the only way that we fix those is through approaches like hot isostatic pressing, basically where you're able to apply high temperature and gas pressure on the part to essentially, modify the internal microstructure. You can squeeze out these internal pores, as well as modify the microstructure. The grains themselves become more isotropic, more uniform, but in that process, they typically grow. And as grains grow, we know that traditionally comes with the trade-off in terms of a reduction of material strength and hardness. In a perfect world, we would both get rid of the porosity while minimizing the reduction in strength and hardness. And that's what these authors are going to try and demonstrate here. Maybe first let's take a look at this graph. This shows you the average grain size as a function of the hipping conditions. On the x-axis, it's the hipping temperature, and then in the different marker colors, you see the different pressures used. And you can see that, as you go to these really high temperatures for hipping, you can get significant grain size increase, right? But you see with the control of pressure going from 1, 10, 50, 100, if you turn up the pressure, then you can reduce that grain size. And so there's a bit of a trade-off available for you in your hipping conditions. So that's exactly what the authors are going to try and introduce, is a framework whereby you can, through modeling efforts, try and actually predict these microstructural changes for pure niobium during post-processing heat treatments like hipping. All right, so one of the cool things that they do here is they're actually going to treat the different grain mobility as an Arrhenius relationship, linking it to both temperature and pressure. Instead of doing a sort of design of experiment or randomly exploring different things, they're actually trying to learn these parameters from the Arrhenius equation so that they can then integrate those into their modeling framework. Here's an example of some of the activation energies for grain mobility when they measure them. You can see now this is showing you the activation energy Q as a function of temperature, and you've got 5 different pressures here. And obviously, pretty significant increase in the activation energy as you go towards higher pressures, right? And that's a big deal. If you look at some of the results here, at 1373 Kelvin, as you increase from 1 MPa to 100 MPa, this leads to a reduction in the grain boundary mobility of more than 70%. So if the grain boundaries are less mobile, then they don't grow as much. If they don't grow as much, then in that condition at 1373, you see a 5.7% increase in the predicted yield strength. Pretty big deal. If you do that at 1273, that strength benefit climbs to 7.6%. So this is a definite way where you can control that trade-off between strengthening and reduction of the internal porosity. A nice way to summarize these results is shown here in figure 4. In figure 4, you see the yield strength as a function of hipping, temperature, and pressures. And there's some subtleties, right? If you take 1073 Kelvin, the benefit that we saw before is actually reduced. As you go from 50 MPa to 100 MPa, that benefit in terms of the strengthening shrinks to less than 2%. So it's nice that they've built a tool here that's going to allow engineers to make relevant decisions about the cost benefit of different pressure or temperatures of the hipping process. Okay, my takeaway from this paper is that they've built a really nice tool here. In the past, people were still doing sort of trial and error optimization, which is not ideal. Instead, what they've now built is a framework that allows you to explore and design these trade-offs and see where the benefit actually makes sense and where it doesn't. And I think it's going to allow us to iterate and model in a more smart and efficient way. I hope you'll read all about it in the latest issue of IMMI.